We are now starting our fourth theme, which will be our last theme today, but it is as well our largest theme. We will have the projects who are directly working into the mining theme, so that will be very interesting. And to start with now is Alessandro Berton from Blekinge Institute of Technology, of course. Hi, Alessandro. I see you there. Hello. In this beautiful forest. I believe you are sitting outside, don't you?
Yeah, seems like, right?
Yeah.
It's a trick for not using a fake background on Teams.
Yeah, but it gives energy. Now we can see your presentation. We can hear you very well. So you have 4 minutes to hold your presentation. Most welcome.
Okay, thank you for introducing me. My name is Alessandro Bertoni, as I said. I'm associate professor at Blekinge Institute of Technology. We are running this project together with our partner company, which is Volvo Construction Equipment. And we are focusing on digital twin-enabled transition to electromobility and autonomy in construction equipment. What do we actually mean with this project? This is a pre-study. It's a 6-month project that where we want to develop system model to trade off economic and environmental performances of different mining sites through the comparing electrical vehicles, fully autonomous vehicle, hybrid vehicles. So being able to simulate the transition toward autonomy and electromobility in the mining sector. In this specific 6-month pre-study, we are demonstrating a first version of a digital twin to support the planning and the design of the future, quarries and mines. And we're also aiming to bring up a pilot project which is involving more companies and more customer sites to develop a larger scale demonstrator of such a digital twin environment. So what we are going so far, what you see here is a screenshot from the simulation environment, which is based on a software called Simio, discrete event simulation software. And here we are combining mathematical modeling of different vehicles that are diesel-driven, battery-driven, or hybrid vehicles, where we bring in vehicle dynamics, battery resistance model, efficiency of the engine, and different inclination and variation of the path that a vehicle has to follow in the mine. And we bring in all this simulation of single vehicle in the broader context of the site or the mine or quarry, where we have simulation of extraction, alternative path to be followed by the machine, even charging station, where to put them, and how many machines are going to be there at the same time. And we're aiming for also linking that to geolocalization, so we can actually have GPS map of the site, telling us where, the altitude at different point on the path, etc., etc. Bringing to what at the end, bringing out a demonstrator, which should and will include more and more companies to be part of the project, and moving beyond the digital twin prototype, but moving into more, I will call it semi-real-time collection of data and communication to the virtual world. So we can still have a constant update of how the mine is looking like and what should be done to improve that. In a very short term, that means the last month now with this pre-study, we are going to finalize the vehicle velocity profile simulations and integrate them better with the battery consumption model and linking that to this discrete event environment, which I showed as a screenshot. And we're also aiming to set up a global optimization routine, actually, to give the simulation some input and let the simulation give us what would be the better optimized solution for the design of the mine, based on the input we give them. That was very short, what we have been doing the last 5 months now.
Thank you, Alessandro, and of course for 5 months working, that wasn't bad at all. So, like you said, you're aiming for a next step, and we are very interesting to see an application, or if you don't go through Swedish Mining Innovation, to hear something from you about that, because very relevant topic, of course.
Thank you.
Thank you again. We will continue, and our next speaker will be Simon Larsson, Luleå University of Technology, and I can see you there, Simon.
Yes, hello everyone. I hope you can hear me.
Yeah, loud and clear.
Perfectly. Then I am going to share my screen. Let's see here. I have this presentation. Okay. Make it into presenter mode. Oops.
Perfect.
You can see my screen now. I hope.
Yeah.
Great. All right. So my name is Simon Larsson. I'm a senior lecturer at Luleå University of Technology, and I'm going to give you a brief overview of our project. It's a pre-study, also 6-month project called Numerical Simulation for Optimization of Rock Drilling and Loading for Mining. And this project is a collaboration between Solid Mechanics at the Luleå University and Boliden also. So the goals of the project is to build some kind of numerical modeling tool that we can use to simulate both drilling and loading. And in this project, this is in Aitik, the Aitik mine in outside Gällivare. And what we do in this pre-study is that we try to demonstrate the strength of using numerical models to understand the really complex environment during both drilling and loading, because you need to consider a lot of different physics here to make it into a correct prediction. And we also try to perform some kind of preliminary validation of our models by experimental measurements in field, in large scale. So what we have done so far, let's see if I can get this to play. I have a video here showing this. Upper left is a drilling model where we have a hammer drill impacting a rock material which breaks, and we can also predict the wear on this drill bit. And you can see this is one of the topics here, the drilling, and also for the loading we have these huge line rope shovels that we use to dig from the muck pile material and load onto trucks. And here we try to predict the flow of this ore from the bucket into the truck, and also to predict the wear on the bucket, so we can optimize the design of the bucket. And we are aiming to create a more advanced model for the rock, because a rock is a very heterogeneous material. So we have performed also some experiments to characterize this rock material under high impact velocities. And we have some preliminary results there as well. And this is basically what we have done so far. Oops. And the goal and upcoming activities is we are aiming to do an application for a full-scale innovation project. And here we will try to further develop this simulator tool. So the aim is that it can be used as an industrial supporting tool when you design this type of equipment for instance, for wear, and also support decisions in the process when you buy your equipment and help the manufacturer. So that's it for me. Thank you.
Thank you very much, Simon, and another, of course, very interesting topic to work with, and where you can do quite a lot for have a better utilization and a more efficient handling. So very interesting, of course. And I believe you and in the same way, and quite a few today, which you start with the pre-study, and then you see if you can have the result and the maybe new partnership you are aiming for to go for a full-size project. So that is very interesting.
Exactly, that has been the idea from the beginning. So
thank you very much again, and good luck.
Thank you all. Thank you.
Our next presenter will be from Örebro University. It is Andrey Kiselev, but he couldn't be here today, so he sent us his presentation. Will you please share it with us, Therese?
Hello, my name is Andrey Kiselev. I'm a researcher at Örebro University. Today I'm presenting a project called Lunar, Learning Uncertainties in Adaptive Remote Mining. So the main objective of this project is to work on safety and efficiency of remote operations of mining equipment. What does that mean is that there are machines out there that are fully manual, traditional machines where you have operator inside. There are machines that are fully autonomous in certain mines where machine basically decides itself what to do and how to do. And then there is a class of machines that are remotely operated. So they do need human involvement due to unstructured environment, due to complex tasks they do, but that operator is located on some distance from that machine. So it could be meters, but it could be kilometers. We have several work packages in the project, and we start with integration and demonstrator platform. We target TRL4, so we use robotic arm that is most suitable for this task to develop the concept of learning frameworks. In work package 2, we targeting learning in manipulation. So we'll look at how robotic arm can adapt its own behavior to dynamic environment and to own changing dynamic models. And in work package 3, we'll look into operator behavior. So we try to understand how much, for instance, operator is focused on the task. If the operator is distracted or not distracted, how much should we trust the control sequences that come from the operator? And then the work planned in the project is full-scale application for Swedish Mining Innovation that would follow. Result so far is that in WP1, we developed simulated robotic environment with a real virtual operator, virtual reality teleoperation interface, and that is because of COVID situation that we didn't have a possibility to work in the lab. So we built a digital twin. So that digital twin will soon be transferred to real lab, and we hope by the end of the year to have it up and running. So in work package 2, we worked on online adaptation to dynamic environments. We have one paper published at CVPR on efficient boiled set registration, and that is fundamental for robotic arm to be able to function. So it can recognize where it is, it can find objects of interest, it can stitch point clouds in an efficient way. And we also have a paper submitted to Transactional Robotics, IEEE TRAN, that is on movement primitives for imitation learning. So that is learning model for robotic arms to figure out the optimal movement trajectories. In work package 3, learning operator behavior, we've conducted massive work on data-driven approach in adaptive autonomy. How do we understand status of the operator in a data-driven way? And that was published as a master dissertation in 2021. This year, so we are currently wrapping up a paper to be published based on this thesis. Our upcoming activities are demonstrated platform, as I said, real deployment in robot lab at Örebro University, and we are in the process of preparing full-scale application together with Epiroc. And the next steps when it comes to scientific objectives is that we want to have expanded experimentation validation of our approach. We would want to go to TL7 level so we can test with real machines, with real operators who actually work in the field. And we also want to do per user training and validation when it comes to machine learning algorithms and data-driven approach to understand operator behaviors.
All right, we thank Andrey for sending in this presentation for us. Very interesting. Now, before the break, which we will have in another 30 minutes, we will have 5 very interesting full-scale projects presented for us. And the first out is Ping Zhang from Luleå University of Technology. So hi and most welcome.
Thank you, Nicholas. Can you hear me?
Yeah, we can hear you, see you, and see your presentation. So let's start.
Thank you. Good afternoon, everyone. Today, I'm going to talk about our project, Destressing Strategies for Mining Under Highly Stressed Conditions in the Deep Mines of Sweden. My name is Ping Zhang, Associate Professor in Rock Mechanics working at Luleå University of Technology. I'm the project leader. The 3 partners involved in this project are LKB, Boliden, Zenkura Mining. This is a full-scale project. We start recently from April 1st this year. A little background. As you can see from these maps, it shows all of the mines in production until the end of 2020 in Sweden. And the red figures indicate the depths of several of mines. As you can see, several of them has mined under they were 1,000 meter and approach 1,500 meter. When you are mining at very high deep level, the stress will be very high. The failure or rock fall you normally see is very bad, is not gradual but occurring in a sudden and violent manner, very difficult to manage. We also know that the main mechanism for this kind of failure is because there is high stress concentration near the boundary of the excavation. When there is any small disturbance, the stored energy will be released, which cause violent and sudden failure. Since we cannot change the stress, so we are wondering if we go deeper, if we could make the stress lower near the boundary by using kind of distressing technology. In this case, we are going to use distress blasting to make the rock fractured and softer. In this case, we make the stress concentration further into the deep rock and to avoid this kind of violent failure. So this is a concept we are going to investigate, distressing blasting technology. To do that, we are going to investigate the construction process of the 3 underground mines on site to understand the rock burst process in the different mines. After that, we are going to evaluate the effectiveness of distressing blasting technique by using numerical modeling and also field tests. After that, we are coming up with a proper design of the blasting pattern, which the mine could use to distress the stress in the excavations. Finally, we hope that we could develop some distressing strategies to mitigate the rock burst risk for the Swedish underground mines. Results so far, and we started the project by recruiting new people, and so far we have 2 master students working on this project and also 1 PhD student recruited. And to conduct the field investigation, we have prepared the questioning layer, which we are going to bring it with us when we do the site interview. And this questioning layer is under review now. And also we have developed the numerical methodology to simulate the blasting by using AirSteiner. We are also going to integrate the result from AirSteiner in another software, which is called UDEC. Then we could understand how the distressing blasting will affect the response of the excavation. Also, we are planning to do a field test at LKB's Kiruna mines. We have discussed with the mining engineers and to see any alternative test sites. We have several selected, but we are going to, we need further confirmation from LKB for 1 test site. And we have ordered, thank you, instruments. Upcoming activities, as for the current situation, we are allowed to travel, so we are going to visit all of the 3 mines this year or at the beginning of the next year, and also investigate the home construction loop. And we are coming up a proper distressing blasting design, which the mine could use for the field test and also instrument the test site. We are going to discuss all of the details in the 2nd workshop scheduled on the 11th November. You are also welcome. That's all. Thank you.
Thanks a lot. And of course, if we will be able to do our operation in those depths in a safe, predictable, and efficient way, I mean, what you are trying to understand here is, of course, very, very important. So, well done,
Niklas.
Thank you. Very interesting, and it will be so interesting to see what your further results will be there. All right, if you stop sharing your screen, ping, and the next speaker is Todor Stoyanov from Örebro University.
Hi, Lawrence. Can you hear me well?
We can hear you and see you.
And I guess you can even see my screen by now.
Yeah, if you can try to have it in another way. Yeah, that is perfect.
All right. So I apologize in advance in case my network drops out. It's not very reliable today for some reason, but hopefully there will be no problems. Thank you for inviting me. Unfortunately, not in person in Luleå. Next year, hopefully, fingers crossed, we can see each other. And today I'm going to talk to you about two projects. The first one is right now. It's a full project, a full-scale project that started in April this year. And the title is Safe Remote Drilling Through the Predictive Modeling of Hydraulic Hoses. Now, what is this project about? It is about machines which do drilling for blasting and for tunnel reinforcement. And these machines are already today partially automated and can follow and execute drill plans. The problem is that parts of the machine are not actually included in these models that we use for controlling them. And this part is actually these hoses that are here colored that hang underneath the booms. Now, this means that we need to control these machines in a very restrictive manner, so very inefficiently, because we do not know where these hoses are. So, for example, it is not possible currently to cross the two arms if you're doing this automatically, simply out of fear that we are going to damage the hoses. So the goals of the project are to actually come up with a better way of modeling how these hoses behave and predicting where they're going to be. And we're going to use for this a combination of model-based and visual state estimation-based methods. And the overall goal is to get increased safety, basically, and allow greater maneuverability. So we did have a pre-study, and I will just show a short video here showing the results from our pre-study, where we tied up one of these hoses to a robot arm and moved it around in the lab. So very small scale stuff that we did last year. But the idea here is to estimate how the hose is going to move. One of these lines, the red or the blue one, is the prediction from the model. The other line was actually the ground truth. So our method worked quite well in this limited test case. What we have been doing so far since the start of the project, we've submitted one more paper now for a robotics conference where we're trying to use these models in order to control how hoses can be moved. This is the video here on the left. You can see our method, which is learning over time to control the motion of these hoses compared to baseline approaches, which works quite well, and we hope that we get this paper through. But it's just the first of several steps we're going to take in the future to get this closer to actually use on the real machines. And to do that, our next steps are actually to set up simulation environment. One of the partners in the project, Algorix, is going to lend some expertise there. And we're also going to simultaneously do a real data collection, which at the and for all of the restrictions to fall, also at our partners at Epiroc, so that we can collect data. And this is it. Thank you.
Thank you, Todor. And very interesting, and of course, to work with safety efficiently in the way you do in this project is very interesting to hear about. So wish you good luck for further work with this project, and we will hear more from you after the break. And maybe then, because it was quite good here with the camera, but maybe then you take it without your own camera, and maybe we have it even better with the sound. But it was good. It was good, but
okay,
maybe it can be better. Okay, next one out is Anna Mannucci from Örebro University as well. Hi, Anna.
Hi, can you hear me?
Yeah, we can hear you and we can see your presentation.
Nice. So yes, welcome everybody. I'm Anna Mannucci from Örebro University. Today I'm going to talk about the Autonomy project, a project in which I work together with Federico Pecora and Eric Andreasson, and with partners Epiroc and Nucleus Mine. Again, let me start by defining a little the project, the background. So today, most mine operation involves LHD vehicles, which are this type of vehicles, transporting rocks from draw points through a set of tunnel till dump points. And most of the operation are actually planned manually with very, very few support tools, which is a source of inefficiency and actually limits the ability of reacting to contingencies. Therefore, the goal of the project is to automate the planning and the control of these fleets of robots, and this can be achieved into sub-goals, the former being developing a global fleet controller to ensure the absence of collisions and deadlocks and to optimize the allocations of missions to robots, and the seconds being designing some tools to support the deployment and the designment of the fleet by itself. So we are almost in the middle of the project, and in the first period we have been accounting for the first sub-goal, so the design of the fleet coordinator, looking through three main directions, the former being formally proving our approach, being safe and live, and we published a TRO paper, and we presented this paper recently. I presented this paper at ICRA, and from a practical point of view, this have led to a new version of our coordination library, which has been widely tested in the Cadia mine that is provided by our Nucleus partner, but also it has supported other projects involving our university, so it was tested on real robot. Since the mine is communication may be quite unreliable in mines, we have been looking at distributing the coordination algorithm. So we did some preliminary tests and we developed a framework which is distributed, but it scales very well, but on the other side, it cannot provide the safe guarantees, the same guarantees of the centralized approach. So we are still investigating the centralized approach. Again, along with this, we have a RAL publication, and it has been presented to the case conference. The third direction of investigation, it was related to optimization methods. And in particular, we have been looking at optimizing the allocations of online posted tasks to fleets of robots. We casted the problem as an online optimization problem, in which we account of the online status of the fleet, and that we solved using an approach that we have been developing, which is systematic and which we compared against other state-of-art algorithms. And this again resulted in a publication that we submitted and published in RAL. With respect to the second sub-goal, we have been developing some tools to support our simulation and the design of a roadmap. For instance, tools that allow by clicking to set some nodes and then to connect them with Bezier curves. And just some few words about upcoming activities and next step. The most important is we are planning an extensive evaluation of our centralized approach, including the target allocation, considering performance metrics, which have been elicited by our Nucleus partner, and integration with our partners, so Epiroc and Nucleus Mine. So thank you for the attention, and here is our contact.
Thanks a lot, Anna, and interesting, of course, to hear about your project, and as well interesting that you are working with, among other partners, our international partner Newcrest as well, because
exactly.
Quite a few in our Swedish mining cluster work with them, and they are one of our strongest international cooperating partner. So very interesting.
Thank you.
Thanks again.
I'll stop sharing the screen.
Yeah, perfect. Next out is Anton Koval from Luleå University of Technology. You are muted, Anton.
Yep. Hello, everyone. Now you can hear me?
Yeah.
Yes, perfect. Okay, I will share my screen.
Yeah.
So all is set, right? You can hear me and see the presentation.
It's perfect.
Yes. So my name is Anton Koval. I'm a postdoctoral researcher at Luleå University of Technology in robotics and AI group. And I would like to present GDrones project, which was established based on the collaboration between LTU, ABB, and Bolide. And I would like to admit that this is full-scale project that has duration of 2 years. And the scope of this project is that in general, the mining industry, it plays really important role for Swedish economy and producing demand in metals. And the main focus is to keep profitability, environmental performance, and safety. And for that, we ended up with this project, and we defined the goals of like developing intelligent mechanism for improving the performance of the Aitik mine. And so the idea behind is that mining process starts from the blasting, and after blasting appears a lot of gases that are toxic. They can be nitrogen oxides or carbon monoxides, and it is really dangerous for human operators to go and inspect there. And also another negative effect is that it creates delays in productions, which is not really efficient. So the idea is to reduce these delays and to increase worker safety by developing a drone solution that will be able to navigate in the open pit mine. You see the concept of the drone navigation, yeah, this is how what we actually attempted to do. So far, we are on the month 6 since the project started, and we are going according to the project plan. And so far in work packages 1 and 2, we completed some basic things like signed project agreement. We established a website for the project, and we designed logo of the project. Next is coming to more interesting activities. So we were focusing on the developments. So we really tightly collaborate with our industrial partners. And so we got definition of correct requirements from them, and based on the estimations, we defined that we can use for navigation as a base platform DJI Matrix 300. For this drone, we will develop autonomy, and so far we designed and integrated onboard computer, designed mount and integrated onboard computer for this drone. And the overall system architecture will include additionally gas instrument, which will be used for measurements of the gas levels in the open pit after blasting. And we have done, actually, we are really happy that we were able to make first tests in the on-site. So we visited Aitik mine and done manual tests, and they proved that we can continue with this with the developed setup. So as a gas sensing element, we're gonna use a dragger instrument, and because it is one of the reasons we concluded with this, it is main gas instrument for gas inspection in the mine. And another point is that comparing with existing solutions, this instrument is the most lightweight. However, we had to sign a non-disclosure agreement with Dragger R&D in Germany, Lübeck. And yeah, this allowed us to establish communication with this measurement instrument and onboard computer.
Anton, 1 minute.
Yeah. Yes, I'm actually finishing. So, and our upcoming activities will be towards development of autonomy and full integration of the gas instrument and integration of aerial platform with the local position system at APIC. Thank you very much.
Thank you, Anton. And another great project description. And when you're working with new solutions, but adding in is existing tools as well, so you don't need to event all by yourself. It's probably very wise to do it in that way.
It is very efficient, and especially in case when it is proven, the efficiency is proven. So some platforms can be used as the research platforms, as we can see now, for example, with Spot robots or with any advanced platforms, but adding our computer on top makes a difference.
Yeah.
Yes, and it makes it easier also for integration, because then we have full control of integration with mine infrastructure.
Excellent. Very interesting to listen to, and very well done. Keep up the good work.
Yes, thank you.
Perfect. Thank you. The last, before our quite short break, the last presenter before that will be very interesting to listen from. It's Shiyu Zhang from Örebro University. So I see you now at my picture. So hi.
Hi, I will share my screen.
Perfect. Yes, working perfectly.
Okay, thank you. Hi, good afternoon. My name is Shiyu Zhang. I'm from Örebro University. Today I'm going to present the progress of the project Autoboomer. The project leader is Federico Pecora, and the partners involved are IPROC, Zengrovan, and Alfred Nobel Science Park. The background of this project is the tunneling process in underground mining. This kind of machines equipped with several drill rigs are used to drill sequence of holes concurrently to help blast rock and dig a tunnel. Today, this process is done manually. The operator needs to assign a hole to be drilled to each arm, then guide the arm to move to the target. So the goal of this project is to automate this process and develop coordination technologies to let multiple robot arms work cooperatively in common workspace. So by doing this, we would like to achieve first to deal with interference among the robot arms, to let them work safely and complete the task. Other than a feasible solution, we also would like to optimize the efficiency to complete the tasks with shorter time and less energy. A particular challenge is we would like to let them have the ability to support online changes and deal with contingencies. Also, we would like to have a good scalability. Current methods in the field have difficulties of dealing all the targets. To fill this gap, we have developed a motion coordination method and the task allocation method. These results have been summarized in research papers which have been published or will be submitted to major robotics journals. First, we consider the target is given for each robot and developed a motion coordination method to generate coordinated motion for the robots. We tested this with a prototype. We simulated the drilling task. use 2 or 3 robots to drill sequence of holes. The robots can update the motion online based on the motion state of the other robots. And by this way, they can deal with contingencies and the safety is guaranteed. We also demonstrated good scalability with linear increase of calculation time. Then we continue consider there is a sequence of tasks to be performed and developed a task allocation method. We tested the method with the same setting. The robots first travel to the target, then stay at the target position for drilling a hole. The duration for drilling a hole is uncertain. We tested random task execution time. The robot system can online calculate the next optimal task to deal with this uncertainty. We can say the robot can move to a target immediately after they reach the last target. There is very little idle time, and they can flexibly deal with uncertain situations. In the next, we would like to test the methods with real boomers and mines, and we will look at the market. Thank you.
Thanks a lot, and of course this one is very interesting, and I know that Epiroc and a few other companies, of course, has struggled with this kind of solutions for quite a few years, and if you can bring it to the next step, it's excellent, of course.
Thank you.
Thank you. Very interesting. Everybody, thank you for watching. We will have quite a quick break, so you can have a cup of coffee and keep your breath, have some fresh air. We will have the pause until 1400. We say most welcome after that, and we will hear more about the theme of mining. We will have some short presenters from the winners from our innovation idea competition, and we will have summary of the day. So we're taking a break now until 1400, and then we will have another about 40 minutes in the program today. So see you within 20. Cheers.